Okay, so now we're going to start our afternoon session. So our first speaker is Yilin Wang from UTH, and she's going to tell us about geometric descriptions of the Loewner.
Thanks, Jason. And thanks for the organizers. I'm very happy to be here again after 3 years. 3 years ago, I was still a master's student. So today I'm going to tell you about what I've been doing in the past 3 years during my PhD. And although you will not see very often the names of Bendeling all the time, but actually I benefit a lot from the discussions with him, and very grateful for it as well. So today I'm going to talk about the geometric descriptions of the Loewner energy. So you are going to see first some background introduction, definitions of the Loewner energy, what we know for the old results about the Loewner energy, where a lot of questions that arises from there. And then in the third part and the White Peterson part, you are going to see the answers to those questions. And the last part will have a lot of more questions. So let me just remind you about the Loewner's idea that he introduced in 1923. The initial goal is to find a way to encode a univalent function from a disk to a simply connected domain. We can also view it as the uniformizing conformal map from the simply connected domain D that is in the plane to the unit disk. So his way is to kind of tracing out the boundary of this domain by a iteration of conformal distortions that to straighten little by little its boundary, and that is called the Loewner flow. And he encodes this flow into a real valued function that is called the driving function. So the study will be with a non-self-intersecting curve that is the boundary of the domain to a real valued driving function W. And this is actually a powerful tool to study the univalent function. For example, it is a tool to solve the Bieber-Bach conjecture that was by Duplanche only 60 years later. And also, as people here are very familiar with, when we take the driving function W to be a multiple of the Brownian motion, then you get the family of non-self-intersecting curves that the Schramm-Loewner evolution that is introduced by Audit Schramm. And in this talk, we will be focusing on the class of function that is in the Cameron-Martin space of the Brownian motion, which means that it has a finite Dirichlet energy. And you can also think this Dirichlet energy as the action functional of the Brownian motion. So it is somehow sitting in between of the classical deterministic world, and also there are some links to the SLE as its natural relation to the Brownian motion of this energy. The first thing we remark is that the action function, if a function has a finite Dirichlet energy, then it will be the curve, the Loewner chain generated by this driving function will be actually quite regular, so it's not as fractal as the Brownian motion. As already the Cameron-Martin space, the function is quite much more regular than Brownian motion itself, as Suraf has pointed out. And then we will call this Dirichlet energy of the driving function the Loewner energy of the curve, just because we use the Loewner's flow to establish the relation between the driving function and the curve. And then you will see its connection to zeta regular determinants of Laplacians and the White Peterson class in the universal Teichner space at the end. So let me just go very fast on the definition. So if you have a core that is sitting inside the upper half plane from 0 to infinity, then you can parameterize it by its capacity. And also, so when we look at the mapping out function of the first bit of the curve and you normalize at infinity, we get the curve again sitting in the upper half plane, and the tip is mapped to Wt, that is the driving function at time t, at capacity t. And W is the driving function of this curve. And we can also recover gamma from the driving function using Loewner's differential equation that is satisfied by this family of conformal maps GT called the Loewner flow. So I want to emphasize on the fact that actually this way to unzip the curve is actually very directional, so that we have to fix infinity and we unzip the curve from the bottom. It's usually, so it's very, you can see there's a very directional nature in this. And some properties of this driving function, for example, start with 0 and it's continuous. There has the scaling property is that if we multiply the curve by a constant c, we just scale it by a factor c, then this driving function will just change under the Brownian scaling. And also the additivity of the driving function, that is, when you map out the first part, the rest has the driving function that is on just the increment of the driving function. And now we look at the definition of the Loewner energy. So we can define the Loewner energy in the setting where you have a simply connected domain D. I always will put the blue color for the boundary of the domain, and the curve itself in black. So here the gamma curve. And then we choose a conformal map, the uniformizing map, mapping this simply connected domain to the upper half plane by sending A to 0 and B to infinity. We choose it to keep the direction from bottom to infinity, from 0 to infinity. And then we just define the energy of gamma in the setting DAB to be the Loewner energy of the curve that is the image by this function phi to be the Dirichlet energy of the driving function. So more precisely, if W is absolutely continuous, you can take the derivative, which is defined almost everywhere, and you take its L2 norm of its derivative divided by 2. And if it is not absolutely continuous, you just take it to be infinity. So this is something that is defined on all the continuous functions. I also want to point out, actually, this there's a variant of the Loewner energy is also considered by Yilin in his paper on the commutation relation. Also, maybe for the similar interest that I will cite later. So here, just remember that how we define the Loewner energy in the simply connected domain is that we have to choose this uniformizing conformal map. But we only fix two boundary conditions, it's 0 and infinity. So there's still a scaling freedom. But actually, we know how does the driving function changes under a scaling. So that is by a Brownian scaling, and we check that actually they give the same value of the energy. So the definition is well defined. It is well defined in the setting of DAB. And also a trivial remark is that if you have a driving function has 0 Dirichlet energy, then it has to be 0 constant function. And what you get is here a straight line, this from 0 to infinity. And in the setting of the simply connected domain, that exactly corresponds to the hyperbolic geodesic. That is the image of the imaginary axis here by this conformal map. And also, this family of driving function has also been considered independently by Peter Fritz and Arthur Shekhar in 2015. And they, for example, they proved a lot of things about the curve generated by the Cameron-Martin space function. And they proved that, for example, when the energy is finite, then the curve gamma is rectifiable. So this is very different than SLE, so it's much smoother. And so this is the first thing that I proved in 2016. This is called the reversibility of the Loewner energy. So it states as follows. If you have a simple chord from D connecting two boundary points from A to B, and then we have this Loewner energy gamma from A to B equals to the Loewner energy of the same curve, but viewed from B to A. So it's a completely deterministic statement, and you can imagine there should be a brute force way to compute this. We get a curve, and you look at this driving function. You, like in the upper half plane case, you just apply z to minus 1 over z. You get another simple curve. You again look at this driving function, and you try to compute that their Dirichlet energy just coincide. However, this is actually quite hard to carry out because imagine that if you have a curve sitting like that, and I perturb a little bit the tail of the driving function, it will not change the beginning of the curve, but it changes what's happened, how it ends. But when we map it by a -1/z, then you start with this dashed curve, and all the conformal maps that follows, they have been already changed. So the driving function itself will be strongly affected if we change the tail of the driving function. So it's very hard to recover what is the driving function of the reverse curve. So how does this proof goes? Actually, I used a very strong result about the reversibility of SLE. So this deterministic result is actually based on the probabilistic interpretation of the Loewner energy to the SLE. Actually, what we know from the Schroeder theorem is saying that the Dirichlet energy of a continuous function is the large deviation rate function of a small multiple of a Brownian motion. And in the SLE setting, so heuristically, what I proved is that the probability of SLE kappa stays close to this curve gamma when kappa goes to 0. This is actually happens very rarely, as you know that SLE kappa will prefer to stay close to the imaginary axis. But if I force it to go close to this curve gamma, then the probability will decay exponentially with the rate function here. That's exactly the Loewner energy of this curve gamma. And then using the reversibility of SLE proven by Jason and Scott and Da Peng, and prove that actually the trace of SLE, we will be only concerned by kappa with small kappa, and the trace of SLE kappa is the same as the law of the SLE when we view it in the other direction. And this is also very natural because SLE rises naturally as the interfaces of scaling limits of statistical models, so where interfaces usually don't have any direction on it. Yeah, so here, since this guy is reversible, if I take reverse of SLE and the reverse of gamma, and they have the same probability, therefore the decay rate also should be the same. So you get the reversibility of gamma. However, to carry out this thing, there are a lot of technical things that I don't want to discuss it today. But yeah.
If you would have another proof of your theorem without using SLE, would you recover the reversibility of SLE?
I don't, but it's actually we're hoping to. I don't know how to do that. Actually, we've been thinking on that. Yeah, but actually, yeah, we can discuss later. Yeah. So that's very curious. For this such a simple identity, there should be a deterministic proof, as Van Song says. But so that's why today that's the main goal of today. So the goal of today is to understand the geometric meaning of the Loewner energy to explain this reversibility of energy. But actually, before that, let's see. In fact, the Loewner energy has even more symmetries than in the caudal case than the reversibility. So then, in a joint work with Stefan Roeder, we consider this generalization of the caudal Loewner energy, that is the Loewner energy of a simple loop. So let's take a simple loop that is sitting on the Riemann sphere. So now you consider this is not only the complex plane, but we add the infinity to it. So you get the actual sphere. You have a curve, black curve on it, and pick a point on this loop, gamma 0, and a very close point, gamma epsilon, close to it. And I look at the complement of this blue curve, that I will consider this as the boundary of the remaining domain. So it's a simply connected domain. And the black part is a chord in this simply connected domain connecting two boundary points that are gamma 0 and gamma epsilon. And then we can define this caudal Loewner energy, as we can do in every simply connected domain. And And then we take the limit when epsilon goes to 0. It is actually an increasing limit, and then it is always defined, can be infinite. That we call the loop energy of gamma, rooted at the gamma 0. I said that it is the loop energy, in fact, generalizes the caudal energy in the following sense. So in the upper half plane setting, you have the boundary is the real line. You sitting in upper half plane, you have a chord. And when we apply z to z square, we map the upper half plane to the complement of the positive real line. You get the curve gamma in it. But actually, I can consider gamma together with its boundary as a loop that is sitting in the domain. And the caudal energy of gamma in the initial domain is actually equal to the loop energy of this gamma together with its boundary. And for example, also trivial thing is that if we have a gamma, the energy of gamma is 0, if and only if this gamma is the straight line, so the positive real line, and you get the perfect circle actually on sitting on the Riemann sphere. And alternatively, actually, we can also encode the loop into a driving function, but this time it's going from minus infinity to plus infinity. And this driving function, depending on the route that you've chosen, and just define its Loewner energy as the Zürich energy of this function. So the theorem that I proved with Steffen is that the Loewner loop energy is independent of the parameterization of the loop. Namely, that if I place the root at some other point, I will still get the same value of the Loewner energy. However, the driving function is completely different. So what does that mean? Is that so here we have the caudal energy of gamma. This is in the complement of this blue part. But if I consider this as a loop, then I can put my root, that is marked point gamma 0 here, and then this part of boundary will become the part of the loop. And this, so it's somehow telling us that the boundary of the domain plays almost the same role as the curve itself. So therefore the Loewner energy has actually much more symmetries than reversibility, and there's you can move even the boundary point around. And therefore we define this energy is actually a Mobius invariant quantity on the set of free loops sitting in the Riemann sphere and vanishes only on circles. And some side result that we had is that if we have the energy is finite, then we have some geometric property. We studied that, for example, gamma has no corner, it's rectifiable, and it's a k quasi-circle with this k depending only on the energy of the curve. And saying that it is a k quasi-circle, it means that it's the image of the actual circle by a k quasi-conformal homomorphism of the Riemann sphere. But we also find examples of curves that is not C1. People might guess it's almost C1, it has no corner, rectifiable, therefore differentiable almost everywhere. But actually there are examples of gamma that is not C1 but has finite energy. And in the other direction is that if we have gamma smooth enough, and C 3/2 plus epsilon, a little bit better than 3/2, then you have the energy is finite. However, the proof is based on the reversibility of the caudal energy and did not tell us more about what does the Loewner energy mean, but however tells us there's much more symmetries. And there's also a gap between the geometric characterization of finite energy loops. Here you see that they are definitely not equivalent. So now we have an upgraded goal, that is to find the geometric description of the Loewner loop energy to explain the parametrization independence, which includes also the reversibility. And also we asked the question about are there if and only if characterizations of family of finite energy loops? So all these questions are yes, and you're going to see many of them. Here you probably see 10 of them. They're all equivalent. Yeah. So you have any question for the definition or? Okay. So now it's the answer. So before we give the answer, let us consider the following functional that I called functional H. And the setting will be actual actually really a sphere on the like S2. And imagine you have a Riemannian metric G that is on the sphere, and the smooth curve gamma separating the sphere into two parts. And then we consider this functional that is like that. So this operator n, it is the operator that acts on the function that is defined on the curve, only on the curve, and from gamma to a real number. So from gamma to R. And what is n doing is that it takes the harmonic extension of these two functions and then take the normal derivative, exterior normal derivative from both sides and add them up. And this is the called Neumann jump operator. It maps a function from on gamma to a function on gamma. And here you see this is the zeta regularized determinant, and here is the length of gamma in the metric G. And here this operator depending on the metric as well, because already to define the harmonic extension, it depends on the conformal class of the metric, and to take a normal derivative also depending on the metric in the neighborhood of the curve. And yeah, the length is well defined because the curve is rectifiable. It's smooth already. Yeah. So what is the zeta regularized determinant? You have heard that already in the talk of Julien. Let me just quickly recall it. It's a way to normalize the determinant of operators. So this operator, the Neumann jump operator, is actually non-negative, essentially self-adjoint. And if we look at the spectrum, it is from lambda 0, lambda 1, lambda 2. The first eigenvalue in the spectrum is 0, because you can take the constant function, it gives you 0 function. And to define the zeta function, we just forget about the lambda 0. We start with lambda 1 and take this sum like the Riemann series. And with the regularity condition on the on the curve, we have this this function can be analytically continued to a neighborhood of 0, and then we define the log of zeta regularization of this operator as minus of the derivative of the zeta function at 0. So why this is called the log of determinant? That is, if we do formally the derivative, then you have the sum of log of lambda I times the lambda I to the power minus s, the derivative in s, and you take formally s equal to 0, then what you get is the log of product of all the eigenvalues. It's like the determinant. So that is why it's called the zeta regularized determinant. And the zeta regularization of determinants has been used by physicists to perform, for example, Feynman path integral, also important in Polyakov's quantum string theory. Yeah. So now this is the theorem. So let me just recall this function h, that is a log of determinant of the disjump operator minus the length of the curve gamma. So if we take the metric to be a metric that is conformally equivalent to the spherical metric G0, so that is the metric that you have in mind for the round spherical metric. This metric is conformally equivalent to this metric G0 is by just multiplying by a scalar that is in front of it. So you can think about this metric as it's not changing the angle of locally, but can changing the length of vectors. And the first thing is that this functional that we define on curves, it is actually conformally invariant. That is, just say that G equals, this functional is the same if I replace G0 by G. The second thing is that the circles minimizes this this quantity, this functional, among all the smooth Jordan curves. And the last one relates the Loewner energy to the this functional h, that I claim that this energy rooted at 0 is equal to 12 times this functional evaluate at the curve gamma minus the functional evaluate at the circle. And this can be also written in the other way as the log of determinant of the Laplacians. So here d1, d2, they are the complement of the sphere S1, the circle S1, and d1, d2, here they are the complement, connected component and the component in the complement of the curve gamma. So already, if we look at this identity, this already gave us the root invariance parameterization independence of the Loewner energy. So in this formulation, there's no root anymore. So that is one of the results that we're seeking for. But however, I have to point out that to define this functional, so for example, to define this z-directly Laplacian, determinant of Laplacian, you need some boundary regularity to make sense of it. So I just stay in the smooth world. And I won't give the proof, but it's essentially the Polyakov conformal anomaly formula that we have to check. They are conformally invariant. I won't say more about it. And for the second point, it's actually immediate consequence of this thing, because here it is a Dirichlet energy, is positive, and therefore circles minimizes this functional H. So I would be just focusing on the last identity. And let's first look at this equality. So how do we pass from the z-directly determinant of this operator n to the z-directly determinant of the Laplacians? So this is a result from Bergelier and Kepler. This stating that basically you can write this functional H like the log of determinant of Laplacian, that is, this Laplacian is on the whole sphere minus the log of volume of this manifold, the sphere, minus the z-directed Laplacian in d1 and d2. Yeah, probably I haven't mentioned that the Laplace Beltrami operator that we take has a Dirichlet boundary condition. So using this result, we just compute the difference of these. And you see these two terms, they vanish, it does not depend on the curve, and so you get this the ratio of the log, log of the ratio. And also, there's also a interpretation of this term, the log of determinant of Laplacian. It is actually can be solved as the total mass of Brownian loops that is contained in the in this manifold M. So the Brownian loop measure is a conformally invariant measure on loops, and that is introduced by Loewner, Greg, and Wendling. And then this equality, that how to interpret this log of determinant as a total mass, this is also the work basically from Yves Lejean and Julien. So if we just have this in mind, this is the total mass in the sphere, and actually minus the total mass of Brownian loop on the M, and we plus the total measure of the loops that is contained in these two connected component of the complement of gamma. Then you have this interpretation that is the difference of H gamma minus HS1 is like the total normalized mass of Brownian loop attached to the circle minus the renormalized mass of Brownian loops attached to gamma. And we will make a precise sense of, there's a way to make precise sense of this equality. I will talk about later after the proof of the previous theorem. So, sorry for this. So now let's look at this identity. We're going to see why the Loewner energy equals to this log. So the first thing that we prove is that if we take this curve gamma to pass through infinity, so it is an infinite curve sitting in the complex plane, and its Loewner energy rooted at infinity can be, there's identity that is like 1 over pi of another Dirichlet energy of the real part of log derivative of a certain conformal map. So this conformal map H is doing mapping this upper part of the curve to a half plane and the lower part also to a half plane. And this is just direct computation. It is also the L2 norm of the pre-Schwarzschild. So this is actually, I will say that maybe at the end, how this actually also has its roots in the quantum zippers idea. So this can be thought as the action functional of the Gaussian free field, and this is the action functional of the SLE. But the proof doesn't use any quantum zipper story. It's a completely deterministic proof. Already, I find this is already a very interesting identity, because here, to define the Loewner energy, we use the flow to straighten this curve gamma. But on the right-hand side, you just take a conformal map at once, and you look at the Dirichlet energy of the conformal map, and you get the identity. So the right-hand side does not involve any Loewner iteration, and it's also in the philosophy of Loewner is to using the driving function to get some information about conformal map. And once we have this identity, we just apply the Polyakov conformal anomaly formula to derive what is this ratio. So what exactly it is. So here there are two cases. One, the surface has no boundary, and if you have a compact surface with smooth boundary, then when you compare the log of determinant of Laplacian with two conformally equivalent metric, then actually their difference can be explicitly written in these two formulas. And for our purpose, the sigma here will be the real part of the log of derivative of h. And so sigma is just this term. And the other term, this k0, there are scalar curvature and this geodesic curvature on the boundary. And anyway, it's explicit. You can compute these things. And we just do the calculation, and we see that this guy equals to this. Basically, all the terms about the curvature cancelled, and we have only the term that is 1/12 pi. Therefore, there's this 12 which appear here, like the difference of these two functional. All right. So as I promised you, and also for those who were in Seoul, I promised you some new slides. So this is the how to make sense of the loop measure attached to the curve gamma and the loop measure attached to S1. So the Brownian loop measure constructed by Greg and Wendelin, it is actually a conformally invariant measure. Therefore, it has infinite mass for small loops, and also infinite mass for large loops because of the conformal invariance. So it's not making sense, because to look at all the loops that are attached to the curve, because they're all infinite. But there's a way that instead of taking the loop, I take the outer boundary of the loop. Therefore, it helps us to get rid of those very big Brownian loop, because if you have a huge Brownian loop, then if you look at its outer boundary, then it will not hit the curve anymore. And to get rid of the small loops, I will look at the intersection of this curve with another circle at positive distance of it, and then the small loops will not appear in the loops that attach in both of them. And this outer boundary of Brownian loops is actually also called Werner's measure. Usually people call it Werner's measure. And as Wendelin has mentioned already today, it is some unique family of self-avoiding loops that's defined on all Riemann surfaces, satisfying conformal restriction and conformal invariance. So they are very natural objects to use to study some property on the Riemann surfaces. And here, if we take the circle and we take a slightly smaller circle by multiplying by 1 minus epsilon, and we look at the conformal map from inside of the circle to the inside of the curve, and this dashed circle will be mapped to an analytic curve that is inside this in here. And the theorem is the following. Actually, for all the Jordan curve gamma, the Loewner energy of gamma can be written as 12 times of the Werner's measure that attach of the loops that attach to both the dashed curve and the solid curve. And it's like doing a cutoff of the curve that is inside this. Yeah. And I don't have time for the proof for it. Sorry. Now let's go to the second part of the answer. Actually, there are other identity of the Loewner energy. So the idea of looking at the curve is that we don't look at the curve itself, but looking at this welding function. So let me just recall you what is maybe it's also new for what is the universal tetranuclear space. So if we take this group that is a quasi-symmetric homomorphism of S1 of the circle, so this homomorphism is called quasi-symmetric if there's a constant for all the theta and t such that the ratio between the distance of image of at equal distance, they are bounded above and below by m and 1 over n. And there's the subgroup of the quasi-symmetric homomorphism that is the Mobius group, that is the Mobius transformation preserving the circle. And the universal tetranuclear space is the quotient of the quasi-symmetric group when we mod out the Mobius transform. So we have already known that in the work with Stefan that we proved that if we have a finite energy curve, then gamma is a quasi-circle, and from the classical theory of quasi-conformal maps, and we know that quasi-circle they are in one-to-one correspondence to the quasi-symmetric weldings. That is well known. So that's why it's very natural to look at what is the welding function for a finite energy curve inside the tetranuclear space, which is the quotient of the quasi-symmetric function on the circle. And by the welding, I mean that if you map the inside of a disk to the inside of the curve, outside of the disk to the outside of the curve, the welding is just the composing f by a g minus 1 you map here, and you take back, you get the homomorphism on the circle. And also, we know that quasi-circles with corners, there are quasi-circles, they have corners, they have infinite Loewner energy, and quasi-circles also can have a Hausdorff dimension larger than 1, and therefore they're not rectifiable, and of course they have also infinite Loewner energy. So quasi-circles is really a very big class, much larger than the finite energy loops. So the question is, what is the class of finite energy loops in the tetranuclear space? So you see the answer here. So let me just tell you what is this class. So it is very well known in the literature that, especially for string series, that the homogeneous space of a C-infinity smooth diffeomorphism inside the tetranuclear space, universal tetranuclear space, that is like that. It has a Kähler structure on it, and string series is interested on this manifold is that it is the parametrization group of the strings. And by Kähler structure, I mean this three structure that are compatible with each other: the symplectic structure, complex structure, and the Riemannian metric. They're all compatible. And actually, there's a unique homogeneous Kähler metric on it, up to a constant factor, of course. So by homogeneous Kähler metric is because here you have a natural group operation on this manifold by multiplying by another diffeomorphism of this one, and you transport locally the picture to the other point, and all the structure, they just look the same at different points. And if we ask this to be a scalar and to be homogeneous, then there's actually a unique one that's called the Weil-Petersen metric. And it actually can be written very explicitly as time is short, and I will just pass it. If you're interested, I can show you later. And then the Weil-Petersen class is just a closure of this smooth part under this metric that is denoted by T01. And this description is given by a lot of people in the late 80s and the 90s, and also 2006 there's the work of Yilin Wang, and even 3 years ago the work by Shen Yuliang. They all work on this class by Peterson. And especially I would like to point out the work by Taktejong and Thiel, that is there's a scalar potential for this metric written in this form. And by scalar potential, I mean that from the potential you can derive the Weil-Petersen metric by taking 2 times derivative in double sense. So everything about the Weil-Petersen metric is already encoded in the scalar potential. So what I proved is that it is also related to the Loewner energy. That is, a bounded simple loop gamma so it is not passing through infinity, has finite Loewner energy if and only if its welding function is in this Weil-Petersen class. Actually, the exact statement that I prove is that this Loewner energy equals to a multiple of this scalar potential. This gives a new characterization of a Weil-Petersen class and also a new viewpoint on the scalar potential on the Weil-Petersen class, or alternatively give us a global way to view the Loewner's driving function, the Loewner's Loewner energy. And also here, in this statement, there's no regularity assumption on the curve, and they are equal. They're really one-to-one in one-to-one correspondence. Yeah, and so also the root invariance. There's no root in the right-hand side. And for the proof of it, actually, I will just be very short. So we just prove, for example, take gamma is smooth, and using this identity, remember we can take any G that is conformally equivalent to the spherical one, and I just choose cleverly a certain metric such that it gives us this identity, and then approximate the general loop by a well-chosen family of smooth curves, as we will have to derive how this energy converges to the limiting curve, and how is the scalar potential converges to the scalar potential of the limiting curve. And that's the sketch of the proof. And just to show you how good this Weil-Petersen class is, this is also the class of finite energy loop, and there are actually even more than these numbers of characterization. They're more or less close or not very close. So for example, here if we know that the L2 norm of the pre-Schwarzian is finite on one side, then it is equivalent to say this is in the Weil-Petersen class, or the other side is enough. Here it is the integrability on the pre-Schwarzian of the Schwarzian of the conformal map. Here is something directly characterizing the curve in terms of the welding, and also related to other classical operators in the geometric functional theory. What is? Sorry, I will be running really fast. So maybe let me just conclude. So what we have seen here is today, for example, the definition of the Loewner energy is the Zürich energy of the driving function, and I used the large deviation principle of SLE to prove the reversibility of this Loewner energy, for example. So it is very naturally related to the Schramm-Loewner evolution. So this question marks relates to the question of Vincent. I don't know. And in this talk, we see that first identity is that this energy is equal to some Zürich energy of conformal map. And this is also naturally related to the large deviation of the quantum surface that is exponential to the square root kappa times the Gaussian free field. And I put this quote marks because that this is the large deviation for the Gaussian field, and I don't know how this works for the measure itself. So maybe here it should be people know better than me. And then it is naturally related to a Gaussian free field partition function, Brownian loop suit. And this, by the work of Yilin, it is related to the zeta regex determinant of Laplacian, and is also in the third part of my talk. We have this link. And both two things are related to the cutoff of Bernoulli's measure of total mass attached to the curve gamma. And then the question is that now we know what is happening in the Weil-Petersen class of the universal Teichmüller space. So what is the random object that is naturally related to it? And there are some questions that I don't know the answer, and if you're interested, I should show all of them. Yeah. So first, for example, what is the random model naturally associated to the Weil-Petersen class? And for me, that will be the welding function, the welding of a natural SLE loop. Maybe that will give an intrinsic description of the SLE loop, at least for kappa less than 4. And if we have intrinsic description of SLE, then it should give the reversibility as well. And also, like the general question, if you know what space belongs to the Cameron-Martin space, the action functional is, so what is the random welding will belong to? And also we see that the Kähler structure of the Weil-Petersen class is very canonical. It is the unique one such that satisfying certain properties. And it is very curious to understand what does that mean in the SLE world. I don't know. And actually I haven't tell you is that this Weil-Petersen class is also having a topological group structure on it, where the universal Teichmüller space does not have this topological group structure. It's only a group, but not the topological one. And for example, the group operation just by composing two diffeomorphisms. So what does that mean in the Loewner setting? It is not clear. And also some work in progress that it's more doable thing. We are deriving a coupling identity between the Dirichlet energies on the field with the Loewner energy. That is the work in progress with Friedrich-Wickland. And other questions, for example, there are natural gradient flow on the Loewner energy, and what does that mean? And the notions of Loewner energy is not specific to the Riemann sphere. It's also, we can also define on the other Riemann surfaces. So you have many equivalent ways to define them, and some of them can be generalized. And so we can ask the question about the generalization. So I would be happy to be able to answer to any of those questions. Yeah, and sorry for running over time. Thanks for your attention.
Do you have any questions for Yilin? Well, if no questions, let's thank you again.
Thank you again.